So that's the story about where we're going with the current data set. But let me conclude then by putting some of these results that I've been showing you back into context. First of all, these measurements of values of omega are a rather striking, can be thought of as a rather striking conclusion of a long scientific history. I mean, you can go back some 2,000 years, and there were already questions about the cosmological parameters formulated in the form of asking if the universe is infinite or not, and whether the universe will last forever. And it's really only been in the last within the last 100 years, that Einstein gave us the conceptual tools to make the question more rigorous. And then, once again, it's only been in the last decade or so that we've actually started to get data sets that begin to address this problem. And I see this as one of the first of this decade's data sets and results that give us surprisingly precise values of cosmological parameters and show much promise in giving even more precise numbers in the near future. And this is only one of a number of techniques that will be doing this coming up. There will be, in particular, this decade will be the period in which the cosmic microwave background radiation will come in with its numbers. And I'll just point out that the measurement that we get, which is particularly strong in this combination of omega mass minus omega lambda, that particular linear combination, happens to be nicely orthogonal to the strongest measurement that you get from the cosmic microwave background, which happens to do its best work in the combination of omega mass plus omega lambda. And although both techniques then have the capability, as I was showing you in our case, to start narrowing in on some single value omega and lambda, it's nice that the two techniques happen to have a complementary capability and get their strongest results in a complementary nature. So this will actually be a very interesting decade in terms of putting together all these cosmological parameters to get these results. And then finally, let me just point out that having a measurement of omega mass that comes in low, if we end up finding ourselves in this regime of around 0.3 in a flat universe, has some rather striking consequences for physics. And in particular, if you consider the flat universe case, the case of the inflationary universe that's favored, a mass of this sort, mass density of this sort, means that the cosmological constant has to be contributed a cosmological constant energy density around 0.7. And this is a substantial vacuum energy density in the universe. And it raises a rather interesting question, because having a non-zero cosmological constant, you now might look in the particle physics theory domain to see, well, what kinds of vacuum energy densities would you expect to find? And the natural place to look would be the Planck mass, where the symmetries are originally starting to get broken. And you find that if you try out what would be an energy density for a Planck mass, you end up with 122 orders of magnitude too much vacuum energy density. So we clearly have a rather small value, even if we have a number as high as omega lambda of 0.7. And the question that then comes back into the court of the theoretical physicist is, how do you get a very, very, very small cosmological constant without introducing a technique which puts in cancellations, for example, with supersymmetric particles, that drives you to a zero cosmological constant? So we really will be raising a rather interesting question for the particle physicist theorist if we have to deal with a substantial cosmological constant or a substantial vacuum energy density. So let me, on